Welcome to another episode of Mastering Cybersecurity, developed by baremetalcyber.com. Let's dive in.
A hard-coded secret often begins as a convenience that looks harmless. A developer needs an application to connect to a database, call a service, decrypt information, or authenticate to another system, so a credential is placed directly where the program can read it. The application works, the test succeeds, and the value may remain there long after the temporary need has passed. The practical problem is that source code and static files are designed to be copied, reviewed, packaged, backed up, logged, and shared, while a secret is supposed to remain tightly controlled. When those two properties are combined, the organization can lose track of who has the secret and where it exists. In this episode, we will answer what makes a secret hard-coded, why that location creates risk, how exposure can spread beyond the original file, and what a defender should do when one is discovered. A hard-coded secret is a password, token, application programming interface, API key, private key, encryption key, or similar sensitive value written directly into source code or another static file. The defining issue is not simply that the value is stored on a computer. The issue is that the secret has become part of content that is normally treated as code, configuration, documentation, or a build artifact rather than as protected secret material. Hard coding ties the secret to the file and often to every copy of that file. It also makes changing the secret dependent on finding and updating all of those copies, then rebuilding or redeploying whatever uses them. A secret stored in a dedicated secrets management system may still be retrieved by an application, but the value is kept separate from the code and can usually be controlled, audited, rotated, and revoked more effectively.
The first major risk comes from replication. Source code rarely stays in one place, and static files are often duplicated through developer workstations, shared drives, backups, test environments, build servers, code review systems, and deployment packages. A hard-coded value travels with those copies, unless a separate process removes it. That means the number of people and systems capable of reading the secret may be much larger than the number that actually needs to use it. The organization may know where the primary repository is, yet have little visibility into old branches, archived projects, downloaded snapshots, or copied fragments. Even when every recipient is trusted, unnecessary duplication increases the chance of accidental disclosure, theft, or reuse outside the intended context. A credential that was meant for one application can therefore become a portable access mechanism carried inside ordinary development material.
Repositories create a particularly important form of persistence because version control is designed to preserve history. Removing a secret from the latest version of a file does not necessarily remove it from earlier commits, branches, tags, forks, pull requests, cached views, or local clones. The visible code may look clean, while the sensitive value remains recoverable from the project's history. Private repositories reduce public exposure, but they do not make embedded credentials safe. Repository administrators, developers, contractors, automated services, compromised accounts, and improperly shared exports may still gain access to the stored history. Public release creates an even wider problem because automated scanners and opportunistic observers can identify exposed keys very quickly. The correct response is not only to delete the text. The secret itself must be treated as potentially compromised because removing evidence of a credential does not invalidate the credential. Application packages and deployment artifacts can expose hard-coded secrets even when the source repository is carefully restricted. Compiled programs, mobile applications, browser-delivered scripts, container images, installation files, infrastructure templates, and configuration bundles may contain strings or resources that can be inspected after distribution. Compilation can change the form of the code, but it does not reliably transform a secret into something protected. Obfuscation may make a value less obvious, yet the application still needs some way to recover or use it. Client-side software is especially unsuitable for long-lived shared secrets because the code and its supporting files are delivered to systems outside the developer's direct control. A secret embedded in a package may therefore reach every device, customer environment, test platform, mirror, and archive that receives the package. Distribution turns one coding mistake into many durable copies. Logs and diagnostic material create another exposure path. Applications sometimes record configuration values, request details, command output, exception messages, or debugging information that includes a credential. A secret may begin in source code, then appear in build output, troubleshooting notes, screenshots, support tickets, monitoring platforms, or copied console text. These secondary locations are often protected less strictly because they are treated as operational records rather than authentication material. Copied code creates a similar problem. A useful snippet may be pasted into documentation, a chat message, a knowledge base, a public question, or another project without anyone noticing that the example contains a live value. Once the secret escapes into these channels, the original repository is no longer the only concern. Defenders must consider the full path the value traveled, not merely the place where it was first discovered. Not every suspicious string in code is a usable secret, and that distinction matters during review. Some values are public identifiers, test placeholders, hashes, non-sensitive examples, or references that cannot independently grant access. A defender should determine what the value is, what system accepts it, what permissions it carries, whether it is still active, and whether additional information is required to use it. At the same time, uncertainty should not become an excuse for delay when the value resembles a real credential. Hard-coded secrets are attractive because they may provide direct access without requiring the attacker to defeat the application's normal authentication flow. Their impact depends on scope. A narrowly limited, expired token is different from a long-lived administrative credential, but both reveal a weakness in how secret material is being handled and governed. We will pause briefly for a transparent promotional message. This episode is brought to you by the Bare Metal Cyber Academy. The Academy is a place for people who want to continue developing practical cybersecurity knowledge through clear, structured education that connects technical ideas to real professional decisions. You can visit DailyCyber.News to explore the Academy and review the learning opportunities currently available. Topics such as credential handling become easier to apply when the underlying concepts, responsibilities, and defensive practices are explained in a direct and organized way. Now, let's return to hard-coded secrets and the controls that reduce their exposure. Keeping a secret outside the source code is necessary, but the replacement method still needs careful design. A configuration file stored beside the application can remain a static exposure point if it contains the same credential and receives the same permissions, backups, and distribution. Environment variables can separate values from code, yet they are not automatically secure, because processes, deployment tools, diagnostic output, or administrative interfaces may expose them. Dedicated secret stores provide stronger capabilities when they restrict access, encrypt stored values, record retrieval, support rotation, and deliver secrets only to authorized workloads. The application still needs an identity that allows it to request the value, so that identity must also be protected. The objective is not to move the same uncontrolled secret to a different file. It is to establish a managed path for issuing, using, monitoring, changing, and revoking sensitive credentials. Secret lifetime and privilege shape the damage that exposure can cause. A credential that never expires can remain useful long after the developer who created it has forgotten where it was placed. A credential with broad permissions can turn access to one file into access to many systems or large amounts of data. Stronger design uses the least privilege necessary, limits where the credential can be used, and favors short-lived tokens or workload identities when the technology supports them. Separate credentials should also be used for development, testing, and production so that exposure in one environment does not automatically compromise another. Rotation is easier when applications retrieve secrets dynamically instead of carrying fixed values inside code. These controls do not make exposure impossible, but they reduce the time, reach, and consequence associated with a stolen secret. Prevention begins by making the secure method easier than hard coding. Development teams need an approved way to request test credentials, access secret stores, configure local environments, and deploy applications without pasting sensitive values into files. Repositories can use ignore rules and protected templates, so local configuration remains separate from tracked content, although those measures should support rather than replace proper secret management. Code review should treat unexplained tokens, passwords, private keys, and connection strings as security concerns, not merely style problems. Automated secret scanning can examine commits, repositories, and build pipelines for patterns that resemble credentials. Training should also explain why realistic sample data becomes dangerous when copied into documentation or examples. The best control set combines usable development practices, technical detection, limited credentials, and clear ownership for responding when a secret is found. Discovery of a hard-coded secret should trigger both remediation and investigation. The first priority is to determine whether the credential is active, and then revoke or rotate it through the system that issued it. Simply editing the file leaves the original value usable. The response should identify where the secret appeared, which repositories and artifacts may contain copies, who or what could access those locations, and whether logs show suspicious use. Historical versions, forks, packages, backups, tickets, documentation, and shared messages may need review. The code should then be changed to obtain the replacement credential through an approved mechanism, and testing should confirm that the application works without restoring the old practice. Finally, the organization should record ownership and improve detection so the same type of secret is less likely to remain unnoticed in future work. Several common beliefs cause organizations to underestimate the problem. One is that a private repository is safe enough, even though access can spread through accounts, clones, integrations, exports, and compromised developer systems. Another is that encoding, splitting, or obfuscating the value protects it, although the application still needs enough information to reconstruct and use the secret. A third is that deleting the line solves the issue, even though version history and distributed copies may preserve it. Some teams also assume a credential is harmless because it belongs to a test environment, but test systems can contain sensitive data, trusted network paths, reusable passwords, or connections to shared services. The correct question is not whether the secret was difficult to notice. The question is whether an unauthorized person or process could obtain a usable credential from material that was not designed to protect it. A practical way to handle this issue is to follow the secret rather than stopping at the first file. Begin by identifying the value and the service that recognizes it. Determine whether it is active, what permissions it grants, how long it remains valid, and which environments accept it. Then trace the locations that may contain the value, including version history, build systems, packages, logs, documentation, backups, and copied code. Revoke or rotate the credential before treating deletion as complete, and verify that suspicious use has not occurred. Replace the hard-coded value with an approved retrieval method that supports controlled access and future rotation. After the immediate repair, examine why the secret was embedded in the first place. A missing developer workflow, unclear ownership, weak review, or unavailable secret management service may otherwise recreate the same problem. A hard-coded secret is therefore not merely sensitive text that happens to appear in code. It is a credential or cryptographic value bound to source code or another static file in a way that causes it to be copied, distributed, retained, and managed like ordinary content. That mismatch is what makes the practice dangerous. Repositories can preserve it, packages can distribute it, logs can repeat it, and copied code can move it into places the original author never intended. The appropriate response is to assume a discovered live secret may have escaped, revoke or rotate it, search for additional copies, review possible use, and replace the design with controlled secret delivery. The durable security decision is to keep secret values separate from the artifacts that developers and systems routinely copy, while giving applications only the limited, temporary access they actually need.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.